are indispensable tools in ensuring efficiency, safety, and reliability in various industrial applications.
Objectives. At the end of this session, you will be able to identify sensors used for monitoring, controlling, and optimizing industrial processes such as load cells, strain gauges, LVDTs, water level sensors, float switches, and float valves, and list the applications of these sensors in various industries. Load cells. Load cells are transducers that convert mechanical force or weight into an electrical output signal. They are commonly used in industrial environments to measure various forces such as tension, compression, pressure, or torque. The output signal produced by load cells is proportional to the applied force, making them essential for monitoring and controlling weight capacity in industrial processes. Several types of load cells exist for varying applications. They are strain gauge load cells, hydraulic load cells, pneumatic load cells, and capacitive load cells. Strain gauge load cells. These are used in scales and material testing to measure weight by sensing how materials bend or stretch. Hydraulic load cells. Found in heavy-duty scales like truck scales, hydraulic load cells measure weight using fluid pressure, perfect for tough industrial environments. Pneumatic load cells. Used in places with explosive risks like mines, pneumatic load cells measure weight by sensing changes in air pressure, ensuring safety. Capacitive load cells. Great for measuring forces in things like car crashes, capacitive load cells work by sensing changes in electrical charge between plates. Strain gauges. A strain gauge serves as a sensor to gauge and track the level of surface strain a material can withstand. When bonded to a stressed surface, the strain gauge deforms or bends in sync with that surface. This causes a shift in the electrical resistance proportional to the strain applied to the surface. Strain gauges are widely employed in various industries including aerospace, automotive, civil engineering, and materials testing to accurately measure mechanical stresses and strains. Let's now see the types of strain gauge. They are linear strain gauges, double linear strain gauges, shear strain gauges, 90-degree strain gauges, half-bridge strain gauges, full-bridge strain gauges, and Rosset strain gauges. Linear strain gauge. Linear strain gauges have one measuring grid and measure the strain in one direction. Only one direction of strain needs to be investigated. Double linear strain gauges have two measuring grids arranged parallel to each other. Typical applications for these strain gauge load cells include taking measurements on bending beams, testing ship hulls and structural components, vehicle testing, construction, railroad applications, and aerospace applications. Shear strain gauges have two measuring grids arranged at a 90-degree offset from each other. Typical applications for these strain gauges include measurements on torsion bars and determining shear stresses as they occur in shear beams like neutral fibers. 90-degree strain gauges have two measuring grids arranged at a 90-degree offset from each other. Typical applications for this strain gauge type include analysis of a biaxial stress state with known principal directions as well as measurements on tension and compression bars. Half-bridge strain gauges. They are specially developed for manufacturing precision load cells that employ the bending beam working principle. They are suitable for applications where the beam length is limited. Full-bridge strain gauges. They have four measuring grids which are arranged so that each is offset to the next at an angle of 90 degrees. Typical applications for full-bridge strain gauges include measurements on tension or compression bars and determining shear stresses as they occur in shear beams. Rosset strain gauges. They are comprised of three measuring grids arranged at an angle of 0 degree, 45 degree, 90 degree, or 0 degree, 60 degree, 120 degree. Rossets are an appropriate choice for analyzing the biaxial stress state with unknown principal directions. Let's now see LVDT or Linear Variable Differential Transformer. A linear variable differential transformer or LVDT is a type of transducer used to measure linear displacement or movement. They consist of a primary coil and two secondary coils wound on a hollow cylindrical core. When an alternating current or AC is applied to the primary coil, it induces a magnetic field in the core. As the core moves linearly within the coils, the magnetic flux linking the secondary coils changes. Applications of LVDT. LVDTs find very wide range of applications in aerospace, test and measurement, and research and development. Water level sensors. Water level sensors employ different principles to indicate the level of water or other liquids present. One common type utilizes a simple conductor to sense the water level. When submerged in water, the conductivity between the two terminals of the sensor changes, allowing it to detect the presence of water at different levels within a container or tank. These water level sensors are versatile and find applications in diverse settings including residential homes, industrial facilities, and hospitality establishments like hotels. Float switch. A float switch operates by utilizing a buoyant float to trigger the opening or closing of an electrical circuit as the liquid level fluctuates. Primarily employed in fluid control systems such as pumps, these switches regulate the flow of liquids by activating or deactivating the associated equipment. Float valve. A float valve is a mechanical apparatus designed to prevent liquid overflow by controlling the flow of liquid into a tank or reservoir. Typically installed at the inlet of the container, the float valve utilizes a buoyant float often housed within a vacuum-sealed container to regulate the liquid level. As the liquid within the tank rises, the float buoyantly ascends with it, guided by the liquid's surface. Once the predetermined liquid level is reached, the float triggers a switch mechanism or directly impedes the flow of the liquid. This action effectively prevents further liquid ingress, thus averting overflow situations.
This brings us to the end of this session. In this session, we have learned to identify sensors used for monitoring, controlling, and optimizing industrial processes such as load cells, strain gauges, LVDTs, water level sensors, float switches, and float valves, and application of these sensors. Thank you for watching. We will see you in the next session. Hello and welcome to this session. Thermocouples are fundamental temperature sensing devices widely used in diverse industries. Operating on the principle of the Seebeck effect, these sensors generate a voltage in response to temperature changes.
Objectives. At the end of this session, you will be able to identify and test the thermocouple with quick test the thermocouple at room temperature, and measure the output of thermocouple at different temperatures. Introduction to thermocouples. Thermocouple is a probe made up of two different metal wires welded at one end. This part is called the hot joint and will be positioned in the space to be measured. The other end is called the cold joint. Let us see the different types of thermocouples. There are three different types of thermocouples used in process industries. They are Type J, Type K, and Type T. Type J. Type J thermocouples are commonly used in the range of -210 degrees Celsius to 760 degrees Celsius. They are less corrosion resistant than Type K but have a higher sensitivity. Type K. This is the most widely used thermocouple type. It covers a wide temperature range and is suitable for general-purpose applications. Type T. Type T thermocouples are suitable for temperatures ranging from 270 degrees Celsius to 400 degrees Celsius. They have good resistance to corrosion and are often used in cryogenic applications. Next, we will look at the tools and materials needed to measure temperature using a thermocouple. You will need the following tools and equipment such as digital multimeter with probes 1 number, steel ruler 1 number. You will also require the following materials and components such as temperature sensors assorted types as required, thermocouple J, K, T and N type sensor 2-wire terminal 1 number each, candle and matchbox 1 number, stand 1 number and marker 1 number. Let us now see the procedure to identify the thermocouple from the assorted temperature sensors. Begin by collecting all the necessary tools and equipment listed for the experiment. Ensure each component is gathered and laid out neatly on the workspace. Before proceeding, conduct a thorough inspection of each part to verify that you have the full set required for the experiment. Pay special attention to any static sensitive sensors. Check the information on the packaging and handle them with care to prevent damage. Here is a safety tip. Some sensors may be static sensitive, so handle them carefully to avoid damaging sensitive components. The next step involves setting up the digital multimeter. Connect the wires in the correct polarity with the red probe to the V ohms milliampere port and the black probe to the common ground, that is COM. Then select the mode on the digital multimeter to display in the low DC millivolts range. With the digital multimeter prepared, connect it across the terminals of one of the type J thermocouple. Ensure correct polarity with the red probe to the red terminal and the black probe to the white terminal. Measure the DC millivolts reading before preheating the thermocouple and record the value in the designated table. Repeat the same procedure for the type K, type T and type N thermocouples. Record the values in the table. Place the candle on the stand. Fix the thermocouple sensor to the stand. Now, light the candle using a matchbox. Carefully heat the end of the thermowell bulb by exposing it to the flame from the candle. Heat it uniformly until it reaches a stable temperature. Once heated, measure the DC millivolt meter reading on the digital multimeter. Then, record your observations in the designated table labeled Table 1. Repeat the same procedure for each of the different sensors. Measure the DC millivolt reading of the type K thermocouple after heating. Record the values in the designated table. Measure the DC millivolt reading of the type T thermocouple after heating. Record the values in the designated table. Also measure the DC millivolt reading of the type N thermocouple after heating. Record the values in the designated table. Note that thermocouple sensors that do not respond to temperature changes are likely to be defective and should be identified as such. Now we will investigate the parts of the thermocouple that is being used. In this experiment, the type of sensor used for temperature measurement is type J. Sensor element material. The sensor element material utilized in this experiment is composed of two dissimilar metals welded together. Number of wires. The sensor configuration consists of 2 wires. Sensor output. Temperature readings in this experiment are obtained in millivolts. Now we will measure the temperature of the thermocouple at room temperature of type J. Take the digital multimeter and set it to the low DC millivolts range. Place the thermocouple in an environment at room temperature. Using the digital multimeter, observe the DC millivolt reading generated by the thermocouple at this temperature. Record the obtained reading accurately in table for future reference and comparison purposes. Next, we will conduct measurements of the DC millivolt readings at various temperatures. To begin, connect the multimeter initially set to the low DC millivolts range. Here is a safety tip. Pay close attention to the polarities of the terminals when making connections. Before proceeding, securely fix the tested thermocouple onto the stand to ensure stability during the experiment. Fix the candle on the stand. Using a steel ruler, mark divisions on the stand to provide reference points for measurements. Make divisions of 10 mm height with 5 divisions marked up to a total height of 50 mm. Light the candle using a matchbox to prepare for heating. Carefully heat the sensing end of the thermocouple using the flame from the candle. Hold the sensing end of the thermocouple near the flame for 5 to 10 seconds. Now observe the DC millivolt reading for the first height, 50 mm, and record the value. This initial reading serves as a reference point for comparison. Next, change the position of the thermocouple to level 2, 40 mm. Hold the position for 5 seconds, observing the DC millivolt readings on the multimeter and record the values in Table 3. Continue by changing the position of the thermocouple to level 3, 30 mm. Hold for 5 seconds, observe the DC millivolt readings and record the values in Table 3. Proceed to change the position of the thermocouple to level 4, 20 mm. Hold for 5 seconds, observe the DC millivolt readings and record the values in Table 3. Finally, change the position of the thermocouple to level 5, 10 mm. Hold for 5 seconds, observe the DC millivolt readings and record the values in Table 3.
This brings us to the end of this session. In this session, we have learned to identify and test the thermocouple with quick test, test the thermocouple at room temperature, and measure the output of thermocouple at different temperatures. Thank you for watching. We will see you in the next session. Hello and welcome to this session. In this video, we will guide you through using RTD sensors to achieve precise heat readings from a lit fire. Explore the fascinating process of temperature measurement in action.
Objectives. At the end of this session, you will be able to verify RTD functionality at room temperature, measure RTD's output DC millivolt at different temperatures. Now let's look at the tools and materials in measuring temperature of lit fire using RTD. For this, you will need the following tools and equipment such as digital multimeter with probes 1 number, steel ruler 1 number. You will also require the following materials and components such as RTD PT100 1 number, candle 1 number, lighter or matchbox 1 number, stand to hold the RTD 1 number, marker 1 number. Let's now see the procedure of measuring temperature of lit fire using RTD. This procedure has 4 key steps. Step 1. Collect and inspect the tools and materials. Step 2. Check RTD sensor at room temperature. Step 3. Heat RTD sensor using lit candle. Step 4. Measure the output readings at different temperatures. Let's look at each step in detail. The first step is to collect all the tools and materials as per the list given. Next, inspect the sensors for any signs of physical damage. This can be a cut of wires or terminals. Here is a safety tip. Handle the sensors carefully to prevent damage. Avoid exposure to water and tapping the sensing part to prevent accidental damage. By following these precautions, we can ensure the functionality of the sensors and preserve their calibration integrity. Next, let's proceed with the verification of the resistance temperature detector or RTD at room temperature to ensure its proper functionality. Begin by preparing a digital multimeter, ensuring that it is set to measure low resistance. Carefully connect the leads of the multimeter to the corresponding terminals of the temperature sensor, ensuring a secure connection. Once the connections are made, note the resistance value displayed on the multimeter in ohms. To observe the variation in resistance, we need to introduce heat to the thermowell bulb. Place the temperature sensor on the stand. This can be achieved by placing a lit candle in close proximity to the bulb. Lit the candle using a matchbox. Observe the multimeter reading as the bulb heats up. Observe the changes in resistance value displayed. This variation in resistance confirms the functionality of the RTD in response to temperature changes. After confirming the functionality of the RTD under heat, it is important to return to room temperature and verify the resistance reading once again. This final verification ensures that the RTD accurately reflects changes in temperature across its operating range. Next, we will proceed with measuring the output at different temperatures to assess the RTD's performance. Begin by connecting a digital multimeter across the terminals of the RTD under test. It is crucial to ensure correct polarity during the connection process. Connect the red probe to the red wire. Then, connect the black probe of the digital multimeter to the white wire of the RTD. Here is a safety tip. Avoid short-circuiting terminals to prevent potential damage to the equipment. Additionally, as some devices generate electricity, handle them with care. Before proceeding further, securely fix the RTD onto the stand to maintain stability during the testing process. Next, place the candle on the stand. Ensure that the RTD is properly marked for reference. Mark divisions of 10 mm height with 5 divisions marked up to the 50 mm height. This marking facilitates precise measurement and observation of temperature changes. Now, prepare to heat the RTD by lighting a candle. Light the candle to take the readings. Here is a safety tip. Exercise caution while handling the direct flame. Keep flammable materials away from the work area and be mindful of any potential hazards. Hold the RTD near the heat source for 5 to 10 seconds to ensure sufficient heating. This duration allows for the RTD to reach an equilibrium temperature, enabling accurate measurement of its response to temperature changes. Next, we will proceed to measure the output readings of the sensor at different temperatures to understand its behavior under varying thermal conditions. Begin by adjusting the sensor's position according to the markings provided. This ensures accurate measurements and consistent observation of temperature changes. Now observe the resistance reading for the first height 50 mm and record the value. This initial reading serves as a reference point for comparison. Next, change the position of the RTD to level 2, which is 40 mm, and note down the readings. This step allows us to assess the sensor's response to incremental changes in temperature. Continue to change the position of the RTD to level 3, which is 30 mm, and record the corresponding readings. This iterative process helps us gather data on the sensor's performance across a range of temperatures. Repeat the procedure by changing the position of the RTD to level 4, which is 20 mm, and recording the readings. Each incremental change in height provides valuable insights into the sensor's behavior under varying thermal conditions. Finally, change the position of the RTD to level 5, which is 10 mm. As temperature increases, change the resistance range. Note down the corresponding reading. This step completes the assessment of the sensor's response to temperature changes across the specified range. These procedures enable comprehensive analysis of the RTD's behavior under varying thermal conditions, facilitating a better understanding of its performance characteristics. After measuring the temperature, ensure to place the sensor in a safe location with care to avoid damage. Handle the sensor gently to maintain its integrity and functionality for future use.
This brings us to the end of this session. In this session, we have learned to verify RTD functionality at room temperature and measure RTD's output DC millivolt at different temperatures. Thank you for watching. We will see you in the next session. Hello and welcome to the session. In this session, we will provide a detailed guide on identifying the components of LED and LCD TVs and understanding how to dismantle them safely. Join us as we navigate the structure and design of these modern televisions.
Objectives. At the end of this session, you will be able to identify the indicators and controls of an LCD or LED TV, remove the back panel cover of the LCD or LED TV, and identify the internal sections and test the TV after finding the faults. Let's first explore LCD and LED TVs. LCD and LED televisions, featuring sleek designs and advanced technology, offer superior performance compared to older CRT televisions. By connecting to the internet via Wi-Fi or Ethernet, these TVs seamlessly transition into smart TVs, offering a world of interactive and connected entertainment experiences. LCD and LED TVs may seem similar, but their main differences lie in backlighting technology and panel thickness. While LCD TVs use fluorescent lamps and typically have thicker panels, LED TVs utilize energy-efficient light-emitting diodes. While there are differences, it is important to note that most components remain the same across both types of televisions. Next, let's see the indicators and controls of LCD and LED TV. The front panel indicators and controls of an LCD and LED TV are power button, input button, home button, OK button, program button, and volume control button. Let us briefly look at each of these indicators and controls. Power button. This button is used to turn on or off the LED or LCD TV. Input button. This button is used to switch between different input sources like HDMI or USB. Home button. This button is used to return the user to the main menu. OK button. The OK button is used to confirm selections. Program button. The program button is used to navigate through different channels or programs. Volume control button. The volume control button adjusts the sound level. Next, let's see the different input or output and audio or video connectors in the TV. These include HDMI or High Definition Multimedia Interface, USB or Universal Serial Bus, AV or Audio and Video, RF or Radio Frequency, Component Video, Optical Audio Out, VGA or Video Graphics Array, Program, and Headphone Jack. Let's look at each of these briefly. HDMI or High Definition Multimedia Interface. HDMI allows for high-definition audio and video signals using HDMI cable. USB or Universal Serial Bus. USB enables connectivity with external storage devices. AV or Audio Video. This is used to connect legacy devices such as DVD players through RCA cable 3RCA 3RCA. RF or Radio Frequency. This is used to connect cable or antenna signals to the TV. Component Video. These connectors are used to transmit high-quality analog video signals, typically in the form of YPBPR or YCBCR signals. Optical Audio Out. This is used to connect TV sound to HD or soundbar and gives best sound clarity. VGA or Video Graphics Array. This is used for compatibility with computer, gaming consoles, and TV. Program. This connector allows for serial communication, including firmware update, remote control integration, etc. Headphone jack. It is used for connecting wired headphones. Let's now look at the tools and equipment required for dismantling the LCD or LED TV. We will need the following tools and equipment. Trainee toolkit 1 set, magnifier lens 1 number, LCD or LED TV 1 number, and set-top box with user manuals 1 number. We will need the following materials and components. HDMI cable 2 numbers, RCA cable 1 set, optical cable 1 number, coaxial cable 1 set. Next, let's see the procedure for dismantling the LCD or LED TV. Keep all tools, equipment and materials ready. Now, let's see how to access the internal components of the TV. To begin, disconnect all cables from the television and proceed to remove the back panel. Locate the screws or fasteners that secure the back panel to the television's frame. These are usually found along the edges of the back cover. Using an appropriate screwdriver, begin unscrewing these fasteners methodically. Keep the screws in a safe place as you remove them, as they will be necessary for reassembling the unit. Carefully lift the cover away to expose the internal components of the TV for further inspection. Here is a safety tip. It is advisable to do this gently to avoid damaging any internal components or the casing itself. Remove the protective cover from the T-con board by unscrewing the screws. Once the back panel cover is removed, you will gain access to the internal sections of the TV, including the power supply unit, main board, and display panel. Let us now locate the internal sections of the TV. Power supply board. Located towards the lower part of the TV, this board is responsible for converting AC input power from the wall socket into DC power, supplying the necessary voltage and current to the TV's internal components. Main board. Usually found at the center of the TV, the main board, also known as the motherboard, is the central processing unit of the television. It controls audio, video, and user interface functions, ensuring the TV operates correctly and efficiently. Speakers. Integrated into the sides or bottom part of the television frame, the speakers are the audio output source, enabling viewers to hear sound directly from the TV. IR and buttons. Situated on the side edge of the TV, this area houses the infrared sensor for remote control reception and manual control buttons, allowing for user interaction with the TV. Panel. The front and most prominent part of the TV, the panel is the display screen that presents images and videos. For LCD and LED TVs, this is where the liquid crystal display or light-emitting diodes provide the visual output. Backlight. The backlight illuminates the display panel, ensuring brightness and visibility of images on the screen. T-con board. Typically placed at the top center or back of the TV, this board manages the timing and control of the display panel, ensuring proper synchronization of pixels for accurate image reproduction. Take time to inspect each internal section carefully, looking for any signs of damage, loose connections, or burnt components that may indicate a fault. As you can see here, there is a cable disconnected from the power supply to the main board. We need to connect it and test the TV. Now let's reassemble the back cover. Carefully align the back cover with the TV's frame and secure it in place by tightening the screws. Ensure the cover is fitted securely without any gaps. Plug the television into the AC socket. Switch on the TV using remote. Check if all connections are secure and that the devices are receiving power.
This brings us to the end of this session. In this session, we have learned to identify the indicators and controls of an LCD or LED TV, remove the back panel cover of the LCD or LED TV, identify the internal sections and test the LCD or LED TV after finding faults. Thank you for watching. We will see you in the next session. Hello and welcome to this session. In this session, we will examine the troubleshooting faults in an LCD or LED TV. Additionally, we will equip you with the knowledge to locate and address issues effectively. Let's begin this informative journey together.
Objectives. At the end of this session, you will be able to identify the no power issue faults in the LCD or LED TV, rectify the fault in LCD or LED TV using the flowchart method, and test the TV after debugging. Let's first look at the tools and materials needed for troubleshooting faults in an LCD or LED TV. We will need the following tools, equipment, and instruments such as Trainee Toolkit 1 set, Digital Multimeter with probes 1 number, Magnifier lens 1 number, Capacitor discharger 1 number, Color pattern generator 1 number, Blower 1 number, Soldering iron 1 number, and Desoldering pump 1 number. We will need the following materials and components: ESD sheet 1 number, soft cloth 2 numbers, HDMI cable 2 numbers, RCA cable 3RCA 3RCA 1 set, optical cable SPDIF 1 number, coaxial cable 2RCA 2RCA 1 set, cleaning brush 1 number, IPA cleaning solution 1 bottle, and fuse 1 number. First, let's test the LCD or LED TV to identify the fault. Keep all the tools and materials required for troubleshooting the TV ready. Begin by positioning the television on the testing table. Now use the remote control to power the television. Switch on the TV using the remote controller. Then check the different patterns using factory reset remote. Observe the front panel of the TV for the LED indicator. If it does not illuminate, this indicates that the television is not receiving power. Now start by placing a soft, non-abrasive cloth on the repair table to protect the television's screen from scratches or damage. Then proceed with the steps to access the internal components. First, ensure the TV is powered off and disconnected from all power sources. Carefully remove all connected cables. Now focus on the back panel cover. Identify all screws that secure it in place. With a suitable screwdriver, methodically unscrew each one, storing them safely for later reassembly. After all screws are removed, gently lift the back panel cover away. Here is a safety tip. It is advisable to do this gently to avoid damaging any internal components or the casing itself. Next, let's get into the troubleshooting procedure. Upon removing the back cover, we are now able to observe the various internal sections of the LCD or LED TV. Take a moment to visually inspect the layout and condition of the internal components, including the power supply board, main board, and connection cables. Refer to the provided flowchart as our guide for systematic troubleshooting. For this, set the multimeter to continuity mode. Using each probe, check the power cord. Listen for a beep or check for low resistance. This signals the cord's proper functionality. Our initial test confirms that the power cord is operational, laying a solid foundation for further troubleshooting steps. Now we will explore the power supply board. First, identify the power supply board within the internal layout of the television. You can recognize it by the array of capacitors, inductors, and connectors typically located near the power input. Once identified, carefully detach the two main cables connected to the board. These are usually marked and may include the main power cable and the cable linking to the main board. Here is a safety tip. Ensure that you gently disconnect these to avoid any damage. Handle the board cautiously due to the fully charged capacitor. Use a discharging tool to safely discharge the capacitor by connecting the cables from the discharging lamp carefully. As the fuse is working in this case, the capacitor won't charge and the lamp stays in an off position. But if the fuse is not blown, the capacitor charges up and then the lamp lights up as the capacitor discharges. Next, we will inspect the fuse. Begin by locating the fuse on the power supply board. It is typically a small cylindrical component, often glass or ceramic, with metal caps on either end. To test the fuse, we will use a multimeter set to continuity mode. This setting helps determine if the fuse has a continuous electrical path. Attach the multimeter's probes to both ends of the fuse. In a functioning fuse, the multimeter should register a change from 1 to 0 accompanied by a beeping sound indicating continuity. However, in our scenario, if the multimeter continues to display 1 without any sound, it signifies a break in the circuit within the fuse. This condition confirms that the fuse has blown and needs replacement. To commence the replacement of the fuse, first we need to carefully remove it from the board. This involves a delicate process of desoldering. Use a soldering iron to gently melt and remove the solder attaching the fuse to the circuit board. Here is a safety tip. Ensure that you apply heat precisely to avoid damaging nearby components. Once the solder is removed, you can lift the old fuse from its position. Now prepare the new fuse for installation. Verify that it matches the specifications of the old fuse in terms of size, type, and current rating. Position the new fuse in place on the board, ensuring correct alignment with the circuit pads. With the soldering iron, apply a small amount of solder to each end of the fuse, securing it firmly to the board. Be sure to create a clean solder joint to ensure good electrical connectivity and prevent future failures. Now let us check if the power supply board is working using a multimeter. So examine the description near the connector of the cable leading to the LCD or LED TV. Ensure that the voltage indicated matches the required specifications for the TV. The same voltage should be visible at the end of the cable when checked. Connect the AC socket to the power supply board of the LCD or LED TV and power it on. Carefully explore and test various voltages to ensure proper functionality. Using a multimeter in voltage mode, place the probes on each terminal of the power supply board and carefully record the readings. If any terminal shows a voltage reading close to 0, it indicates the need for power supply board replacement. In power supply board testing, only 3.5 volt pins come alive. Next, proceed to conduct a thorough inspection of the main board. Connect the main board and backlight cables to the power supply boards. Then connect the AC socket to the power supply and switch it on. Next, using a TV remote controller to power on the television, closely observe whether the LED light turns on. The activation of the LED serves as a confirmation of the main board's proper functionality, ruling out any potential power-related issues. Sometimes you may encounter a no display issue despite completing prior troubleshooting steps. In such a case, refer to the provided flowchart as a systematic guide for further diagnosis. Begin by confirming the functionality of the power supply board, ensuring all voltages including the 24 volt. If the power supply board is operating correctly, proceed to inspect the functionality of the power button on the front panel. Replace if found faulty. Next, assess the performance of the IR receiver. Replace if necessary to restore signal reception. Lastly, verify the main board for any signs of damage or malfunction, ensuring all connections are properly secured to facilitate TV startup. With all previous tests affirming the correct operation of the TV, it can be confidently concluded that the device is in optimal working condition. Now let us reassemble and test the TV. Use a screwdriver to securely attach the back cover onto the TV. Position the TV upright on the table, ensuring stability. Verify that the patterns displayed on the screen accurately correspond to the selections made using factory reset remote.
This brings us to the end of the session. In this session, you have learned to identify the no power issue faults in the LCD or LED TV. Rectify the fault in the LCD or LED TV using the flowchart method. Test the TV after debugging. Thank you for watching and see you in the next session. Hello and welcome to this session. In this session, we will tackle no picture and no sound issues in the LCD or LED TVs. Through hands-on exploration, you will sharpen your skills in troubleshooting and assembly of LCD and LED TV. Let's get started.
Objectives. At the end of this session, you will be able to identify no sound and no picture issues in the LCD or LED TV, rectify the fault in LCD or LED TV using the flowchart method, and test the TV after debugging. First, let's test the LCD or LED TV to identify the fault. Keep all the tools and materials required for troubleshooting the TV ready. Begin by placing the TV on the repair table. Connect a set-top box to the TV using an HDMI or 3RCA cable, ensuring both power cords are securely plugged in. Press the power button on the remote control. If the front panel's red LED lights up but there is no display or sound, it indicates a potential issue with the TV's audio and visual components. Then, lay a soft cloth on the repair table to protect the TV's surface. Disconnect all cables connected to the TV to ensure safety and ease of access to its internal components. Gently remove the screws holding the back panel cover in place, taking care not to damage the surrounding areas. Once the screws are removed, carefully lift the back panel cover to reveal the internal sections of the TV. Take your time to avoid causing any unnecessary stress to the components. Next, let's get into the troubleshooting procedure using the flowchart. To perform the cable and speaker test, refer to the provided flowchart. Begin the speaker cable test by identifying the connector from the mainboard and carefully disconnecting the cable linking the mainboard and speaker. Utilize a multimeter set to continuity mode to test the speaker cable. Start with the left side. A reading of approximately 5 ohms on the multimeter, accompanied by sound output, confirms the cable's functionality. Once the integrity of the cable is verified with the mainboard and ICs confirmed as operational, redirect your attention to testing the speaker unit itself. Switch the multimeter to resistance mode and focus on testing the left speaker. Ideally, the reading should hover around 8 ohms, specifically tailored for this speaker model. In some instances, speakers with a reading of 4 ohms may also be compatible. However, if the multimeter displays a reading of 2 ohms, it signifies a deviation from the expected resistance level, indicating a need for speaker replacement. Repeat the testing process for the right speaker using the same method. If the multimeter registers a resistance value outside the acceptable range, it indicates a malfunctioning speaker. In such cases, immediate replacement is necessary. If there are problems with the mainboard, then replace the mainboard. Any malfunction or damage to the audio jack interface on the mainboard can disrupt the sound output, leading to the observed symptoms. In such cases, replacing the mainboard becomes imperative to resolve the issue effectively. Referring to the provided flow diagram, follow the designated steps for mainboard replacement to address the underlying issue. Next, let's troubleshoot the no picture issue for the LED TV. Begin by identifying and carefully disconnecting the back LED light connector from the power supply board. Utilize an LED tester to assess the functionality of the LEDs. Ideally, when the LED tester is connected to the backlight, it should display a voltage reading of approximately 72 volts. This voltage indicates that the LEDs are operating within the expected range. However, if the LED tester consistently displays a voltage reading of 300 volts instead of the expected 72 volts, it suggests a fault within the LED lighting system. Such a discrepancy in voltage levels indicates a malfunction or failure of the LEDs, resulting in improper backlighting. In this case, where the LED tester registers a voltage reading of 300 volts, it confirms that the LEDs are indeed faulty. This diagnosis highlights the need for further inspection and potential replacement of the defective LEDs. For further testing and inspection, it is essential to begin by disconnecting all cables connected to the T-con or timing controller board. Next, carefully flip the TV over to access the front side. Gently remove the front plastic panel cover from all sides of the TV. Safety tip: take care to handle the panel with caution to avoid causing any damage to its delicate structure. Once the front panel cover is removed, place the display screen on a soft cloth or a padded surface to prevent any scratches or damage. With the display screen secured on the soft cloth, proceed to remove the different layers of diffusers positioned behind the screen. Additionally, remove one layer of reflector material to gain access to the LED strips and cables located beneath the diffusers. Finally, carefully unplug the cables connected to the top of the LED strip. Examine the LED strips and cables closely for any signs of damage, wear, or malfunction that may be affecting the TV's performance. Next, utilize an LED tester to assess the overall function of the LED strip. Following the overall function test, proceed to check each LED individually along the length of the strip. During the individual LED inspection, if any LED fails to light up or exhibits irregularities in illumination, it indicates a malfunctioning LED that requires replacement. In such cases, it is advisable to replace the entire LED strip rather than attempting to replace individual LEDs. When replacing the LED strips, it is recommended to use strips from the same brand and specifications as the original ones. This ensures compatibility and consistency in performance, maintaining the quality of the display and backlighting system. Now let us see how to replace the backlight of LCD. If the LCD TV's backlight is malfunctioning, test it by connecting the power supply. If it is not working, disconnect the power supply and carefully replace the old backlight with a new one, ensuring all connections are secure. Once done, reassemble the TV and enjoy improved picture quality. Now we will reassemble and test the TV. Start by carefully connecting the reflector, diffusers, front panel and display. Once the front components are securely in place, gently flip the TV over and connect the cable to the T-con or timing controller board. Here, you will find the back LED cable. Connect this cable to the power supply board of the TV with precision. Now it is time to attach the back panel. Slide it into position, aligning it carefully with the edges of the TV casing. Once aligned, use the provided screws to secure the back panel firmly in place. Now that the assembly is complete, let's move on to testing. Carefully place the TV on the stand, ensuring it sits securely and evenly. Next, it is time to connect the set-top box to the TV using an HDMI or 3RCA cable. Now plug both the TV and the set-top box power cords into the AC socket. Ensure the cords are securely inserted and there are no exposed wires. Once the cords are connected, switch on the power to both the TV and the set-top box. With the power on, grab the remote control for the TV and press the power button. Take a moment to verify that the display is working correctly with no visible defects. Now let's test the sound.
This brings us to the end of this session. In this session, you have learned to identify the no sound and no picture issues in the LCD or LED TV. Rectify the fault in LCD or LED TV using flowchart method. Test the LCD or LED TV after debugging. Thank you for watching and see you in the next session.
Hi, Namaskar and very welcome to all of you. Today I am going to discuss some of the important points to keep in mind during planning of multi-story building or high-rise building. There are proper guidelines and policy issued by ENC's branch for planning of multi-story